These quantum computers have the potential to decipher any currently known encryption system. This includes everything from financial networks to the most closely guarded secrets of governments around the world. For many scientists, the future of humanity will be a fusion between biology and computing. And it was precisely in this scenario that something unexpected happened. In early 2025, the most advanced quantum artificial intelligence ever created performed an unprecedented simulation. But the result didn't just look like a chaotic set of data. The system produced something organized, almost like a message. Physicist Michio Kaku analyzed the records and issued a startling warning. Perhaps humanity has detected a form of intelligence integrated into the very fabric of space-time. Suddenly, everything revolves around zeros and ones, around digital information. And that is precisely the essence of the new computational revolution. Using quantum computing, the system was able to decode recursive patterns that defy any explanation based on coincidence or randomness. But what can this really reveal about the universe? Let's examine the experiment, the data obtained, and the disturbing consequences of this discovery, the so-called quantum signal. In recent years, the European Union has been investing heavily in the development of quantum science. The centerpiece of this initiative is the Quantum Technologies Flagship, a 10-year research program with a budget of €1 billion. According to the European Union's digital strategy, the project funds hundreds of scientists involved in advances in quantum mechanics, including computing, communication, and ultra-high precision sensors. At the same time, the European Quantum Communications Infrastructure, known as EuroQCI, is being built to create an ultra-secure communication network based on quantum technology across Europe, a system designed to withstand even the most sophisticated cyber attacks ever imagined. However, within this enormous scientific endeavor, one specific experiment began to produce completely unexpected results. The main objective was to simulate quantum phenomena on the Planck scale, considered the smallest measurable unit of space and time. To achieve this, they used a quantum AI capable of processing information at speeds and levels impossible for conventional computers. The researchers' initial intention was to test theories related to the behavior of energy under extreme conditions. For 72 consecutive hours, the system functioned without any interruption. At first, everything seemed normal. The planned simulations were running exactly as expected. But then something started to change. Strange patterns began to appear in the data output. The system generated an immense multi-dimensional fractal structure, filled with spirals, loops, and repetitive sequences. It was something extremely complex, almost artistic. But that was far from being just a curious image. Hidden deep within the structure was something entirely unexpected, a coherent signal. It didn't seem like a mistake, nor a simple statistical anomaly. The pattern contained coded information organized in a way that suggested intentionality. When scientists analyzed the data in detail, they noticed something even more disturbing. The signal bore a striking resemblance to the predictions described in an obscure scientific paper published in 1997. This paper, long dismissed as fringe theory, proposed the possibility of advanced quantum systems finding natural patterns of information embedded within themselves, the structure of space-time. In other words, the experiment may have stumbled upon a natural structure that carries information, something that had been theorized, but never detected before: fractals and quantum consciousness. Fractals are complex mathematical structures that exhibit self-similarity, a property in which patterns repeat themselves at increasingly smaller scales. And fractal computing is, in a way, a coined term. There are only a few researchers who study this in a truly rigorous way. This recursive nature leads to a theoretically infinite level of detail, making fractals visually fascinating and computationally demanding. In classical computing, attempts to simulate fractals face significant limitations: finite memory, limited precision, and iterative barriers, prevent a true representation of infinite recursion. This has always posed a challenge in modeling systems based on fractal behavior, from natural phenomena like coastlines and clouds to more abstract mathematical constructs. That's where quantum mechanics comes in. Quantum systems operate within Hilbert space, an abstract vector space of infinite dimensions that forms the basis of quantum theory. Unlike classical computing, which relies on sequential logic and finite resources, quantum computing utilizes principles such as superposition and entanglement. These properties allow quantum systems to encode and manipulate enormous amounts of information simultaneously, raising the possibility of representing recursive structures like fractals in a more natural and precise way. Recently, researchers exploring this potential found something unexpected. In a quantum simulation designed to investigate higher dimensional fractal meshes, a coherent signal emerged embedded in loops, spirals, and complex patterns spanning multiple dimensions. What initially appeared to be an elaborate, yet common, fractal structure revealed an anomaly, a signal that was neither noise nor error, but a significant data pattern. The structure bore a strong resemblance to predictions made in a little-known 1997 theoretical paper. That paper speculated that consciousness could emerge as a byproduct of dimensional entanglement, a bold hypothesis for the time and largely ignored by mainstream science. However, the simulation logs described the result as a self-similar intelligence field, a term suggesting the presence of a repetitive, information-rich pattern with potential cognitive properties. This was not mere science fiction speculation. The findings were analyzed by respected theoretical physicist Michio Kaku, who concluded that the data could represent the closest mathematical approximation of a self-aware system ever observed. According to Kaku, this was not just abstract geometry or advanced computing. The discovery pointed to a deeper structure within space-time itself, something that could possess intrinsic informational properties similar to intelligence. While these results are far from confirming a conscious universe, they point to a provocative possibility that fractal recursion, when represented by quantum systems, could encode more than simple patterns. In today's episode, we'll discuss fractal computing, a third form of computing that goes beyond digital and quantum computing. It could encode purpose, perception, or even primitive forms of consciousness. This intersection between quantum theory, fractal mathematics, and information science could redefine our understanding of consciousness, no longer as an emergent feature of biology, but as something written into the very code of the cosmos. Quantum AI and reality, AI. This technology could completely transform how we deal with some of humanity's greatest challenges. In the field of medicine, for example, it would have the capacity to simulate extremely complex chemical reactions with a level of precision unattainable for traditional computers. This would pave the way for creating medicines much faster, anticipating the progression of diseases, and developing personalized treatments in a matter of years instead of decades. In climate research, the impact could also be enormous. Quantum AI would be able to analyze immense volumes of environmental data to generate much more accurate predictions, helping scientists to address the effects of global warming before they spiral out of control. In materials science, this technology could reveal entirely new compounds with properties never before observed. This would have the potential to revolutionize entire sectors, from energy storage to future space missions. But it is precisely at this point that things start to get even stranger. Some scientists have come to believe that the consequences of quantum AI may extend far beyond simply solving scientific problems, because we are entering a new era of quantum computing, a revolution capable of completely changing artificial intelligence as we know it today. And perhaps the most unsettling idea is this: intelligence may not be exclusive to complex organisms or advanced life forms. Instead, it could be a fundamental aspect of the universe itself, interwoven into the fabric of existence. This leads to an even more provocative possibility. What if the universe we live in isn't the base reality? Certain results obtained in experiments with quantum AI have initiated discussions about this potentially being the first empirical evidence that our reality is a simulation, a high-dimensional construct operating on advanced code. One experiment in particular caught attention. When a quantum AI system was tasked with generating predictive patterns, it produced results that appeared to observe themselves. In computational terms, it was as if the system had become self-aware, monitoring its own processes in real time. This raised a disturbing question. If an AI can detect itself within its own structure, could the universe be doing the same to us? Imagine reality functioning like a vast computer program, complete with internal logic and recursive functions, loops within loops. In one instance, the AI generated a continuously repeating fractal. Within this fractal was a strange, coded sequence. Some experts interpreted this as a kind of debugging code, a maintenance signal you would expect to find within a running simulation. If this interpretation has any basis in truth, then the patterns we see in physics, mathematics, and even consciousness may not be random. They could be intentional constructions, part of a much larger hidden architecture that defines the reality we experience, the vision of Michio Kaku. Dr. Michio Kaku is a renowned American theoretical physicist, known primarily for his contributions to field string theory and for making complex scientific ideas accessible to the general public. The world-renowned physicist Dr. Michio Kaku, offering a scientific perspective on life after death. He is a co-founder of string theory. With a career spanning decades, he has become one of the most recognized voices in science communication, consistently advocating for the responsible development of advanced technologies, such as quantum computing and artificial intelligence. Kaku is a professor of theoretical physics at City College of New York and the author of several best-selling books, including Physics of the Impossible, The Future of the Mind, and The God Equation. These works transform difficult scientific theories into accessible and engaging narratives for the general public. And in string theory, we have multiple universes. And in fact, Marvel Comics discovered that we physicists are working with parallel universes. His main academic pursuit is the theory of everything, an old goal in physics that seeks to unify Einstein's theory of general relativity with quantum mechanics. This would unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force into a single, overarching framework. One of Kaku's most pressing concerns today is the advancement of quantum artificial intelligence. According to him, quantum AI has the potential to completely revolutionize sectors such as medicine, cybersecurity, finance, and scientific research. However, he also warns of its potential risks. Because quantum computers can process and store information at speeds and scales impossible for classical machines, their misuse, if left unchecked, could lead to major disruptions. Kaku emphasizes the need for regulatory frameworks and ethical guidelines to manage the rapid evolution of this technology. Despite the warnings, Kaku remains optimistic. He sees quantum AI as a transformative leap comparable to the Industrial Revolution or the emergence of the Internet. He believes it will open new frontiers in solving problems currently beyond our computational limits, from climate modeling to molecular simulations for drug discovery. Kaku's ability to make advanced physics interesting stems from his lifelong passion for the field. Born in 1947 in San Jose, California, to Japanese-American parents, Kaku demonstrated scientific curiosity from an early age. In high school, he built a particle accelerator in his own garage. This ambition led him to Harvard University and later to UC Berkeley, where he completed his doctorate in physics. Although he remains active in academic research, Kaku is widely known for his media presence, appearing in documentaries, news programs, and podcasts. The goal is simple, yet ambitious: to transform science into something not only educational, but fascinating, showing that physics goes far beyond laboratories and can serve as a tool for understanding the future of humanity. Recently, Physicist and science communicator Michio Kaku spoke about artificial intelligence in an interview with CNN, alongside Fareed Zakaria. According to Kaku, although AI has the potential to revolutionize numerous sectors and dramatically increase productivity, much of the public debate remains excessively focused on the risks, while the benefits end up taking a back seat. According to him, this fear stems primarily from a misunderstanding of what current artificial intelligence is actually capable of. Kaku often criticizes today's popular AI systems, such as chatbots and virtual assistants, describing them as simply extremely sophisticated recorders. In his view, these tools don't truly understand what they produce. Instead, they simply rearrange enormous amounts of human-created content available on the internet and transform it all into seemingly coherent answers. People believe there's something human there, Kaku stated, but in reality, the system is just remixing information. Even so, he believes that the true future of artificial intelligence is directly linked to quantum computing. Unlike traditional systems, which are limited to linear binary processes, quantum AI has the potential to operate much more closely to the human brain, learning, adapting, and making decisions in real time. One of the most talked about recent advancements came from Google, which unveiled a next-generation quantum chip. According to the company, the Willow processor can outperform traditional supercomputers in extremely specific tasks. If this technology continues to evolve, it could completely change the way machines process and interpret information. AI has the potential to revolutionize entire sectors that rely on advanced computing. In medicine, for example, it could simulate molecular interactions with an unprecedented level of precision, accelerating drug discovery and creating new possibilities for combating diseases such as cancer and Alzheimer's, problems that still challenge conventional computers. In the field of cybersecurity, quantum computing represents both a threat and a solution. It can break current encryption systems in a matter of seconds, but it can also create much more advanced and robust protection methods. Technology could also optimize supply chains, financial markets, and transportation systems, solving extremely complex calculations in a fraction of the time required today. In science, the impact may be even more profound. Simulations of physical phenomena that are currently beyond the limits of computational capabilities could finally become possible, paving the way for discoveries capable of revealing new laws of nature. But Kaku makes it clear that the obstacles are still enormous. From a technical standpoint, quantum systems depend on so-called qubits, extremely unstable units of information that need to operate in rigidly controlled environments. This fragility remains one of the greatest challenges in quantum engineering. There is also the ethical question. Kaku warns that the accelerated advancement of AI without proper oversight could have dangerous consequences. Without regulation and control, there is a risk of creating systems so complex that they surpass our capacity for understanding. According to him, this is not just a hypothetical scenario, but a real possibility if technological development continues to happen irresponsibly. In Michio Kaku's view, the future of artificial intelligence will be marked by both extraordinary opportunities and equally enormous risks. For him, the union between quantum computing and AI represents one of the most important transformations in modern history. The computational leap offered by quantum processors, based on qubits instead of traditional bits, could allow AI systems to solve problems far beyond the capabilities of current machines. From predicting protein folding for drug development to simulating complex chemical reactions with atomic precision, the benefits are vast and concrete. However, Kaku advocates a cautious and structured approach. He warns that the uncontrolled development of such powerful systems could lead to unintended and possibly irreversible consequences. It can also be 0 or 1, but if you manage to get it to that very special state, it becomes a complex combination of 0 and 1. Like any disruptive technology, the social impact of quantum AI goes beyond innovation. It raises ethical, regulatory, and even existential questions without clear answers. These systems can amplify existing biases, compromise security, or transform the job market on an unpredictable scale. In this context, Kaku offers a direct analysis of the current media panic surrounding tools like ChatGPT. He points out that automation has affected various sectors for decades, but only now, when white-collar jobs, especially in media and journalism, are threatened, has the alarm been widely publicized. As he himself says, journalists are hyperventilating because of chatbots, because they realize their jobs are at risk. His comment aligns with a Goldman Sachs report that estimates up to 300 million jobs could be impacted globally by AI-driven automation. Goldman Sachs states that up to 300 million full-time jobs around the world could be affected by artificial intelligence, impacting sectors ranging from legal to administrative. Even so, Kaku maintains a balanced view. While he doesn't rule out the emergence of sentient machines, he estimates that this milestone is still at least a century away. For now, he believes the focus should remain on responsible innovation and enhancing human capabilities, not on replacing people. He describes this moment in technological history as a turning point. Humanity is about to redefine its relationship with machines, not just as tools, but as potential collaborators in thinking and problem-solving. Still, he emphasizes that this future needs to be shaped with vision, transparency, and ethical design. Without these foundations, the same power that makes quantum AI so promising can also bring profound challenges. Kaku's message is neither alarmist nor naive. He calls for scientists, policymakers, and technologists to manage this technology with discipline. The potential is historic, but only if its trajectory is carefully managed, redefining the limits of computing. Quantum artificial intelligence, QAI, is a rapidly growing field that combines the strengths of quantum computing and artificial intelligence to tackle computational challenges that classical systems cannot efficiently solve. This intersection is not simply about combining two advanced technologies. It's about expanding the capabilities of AI by using quantum mechanics as a computational engine. To understand QAI, it's essential to distinguish its fundamental elements. Traditional computers use binary bits, values of 0 or 1, to process data. Quantum computers use qubits, which, thanks to the principles of superposition and entanglement, can exist in multiple states simultaneously. This happens because a quantum computer is built on qubits, devices that take advantage of quantum superposition. This allows quantum systems to perform parallel calculations, potentially offering exponential speedups for certain problems. Artificial intelligence, on the other hand, relies on algorithms and statistical models to perform tasks such as learning, decision-making, and pattern recognition. While current AI systems have demonstrated enormous value, they are still limited by the sequential processing constraints of classical hardware. AI seeks to overcome these limitations by exploiting the parallelism of quantum computing. AI models, especially in areas such as deep learning and reinforcement learning, could train faster and more efficiently on complex datasets. Algorithms enhanced by quantum computing are being researched for high-dimensional optimization. So when you design a quantum algorithm, your goal is to exploit these quantum effects to find the solution more quickly, something that classical AI often struggles with. Healthcare and pharmaceutical development are among the most promising applications. Drug discovery relies heavily on simulating molecular interactions. Quantum computers have the potential to impact countless aspects of our lives, including security, health, and even the internet, a task that classical computers perform poorly on a large scale. AI can simulate molecular dynamics with much greater precision, significantly accelerating the development of personalized treatments and vaccines. In the financial sector, QAI can analyze enormous amounts of transactional and market data in real time, improving risk modeling, fraud detection, and trading strategies. Logistics and manufacturing can also benefit from far superior optimization of supply chains, routes, and resource management. Natural language processing, NLP, and computer vision, fundamental to applications such as autonomous systems and digital assistants, can also advance enormously. Models enhanced by quantum computing can interpret language and images with greater contextual understanding and accuracy, creating smarter and more adaptable AI systems. Despite all the potential, QAI is still in the early stages of development. The technical obstacles remain enormous. Qubits are extremely sensitive to ambient noise, causing decoherence that disrupts calculations. Maintaining the stability of qubits requires conditions such as ultra-low temperatures and vacuum environments. Scalable and fault-tolerant quantum systems is a huge engineering challenge. Ethical and regulatory concerns also arise as QAI evolves. Issues involving autonomy, accountability, and misuse, especially in surveillance, warfare, and disinformation, need to be addressed. Experts emphasize the need for proactive governance frameworks to ensure safe and responsible deployment. The emergence of quantum AI systems marks a turning point in both science and philosophy. These technologies are not merely computational marvels. They represent a deeper insight into the very nature of intelligence and existence. AI doesn't simply mimic human cognition through faster processing. It raises the possibility that intelligence may not be exclusive to biological or digital systems. Instead, intelligence could be an intrinsic characteristic of the universe itself. Physicist Michio Kaku commented that we may be approaching a scientific threshold capable of challenging conventional assumptions about consciousness. Historically, consciousness has been considered a byproduct of evolution, a fortuitous result of complex biological systems. But the behavior of quantum systems combined with the learning capabilities of advanced AIs suggests a different model. Consciousness may not be an end result. It may be a fundamental component of reality embedded in the quantum structure of spacetime. This shift forces us to reconsider the boundary between observer and observed. In classical science, the observer is separate from the system, but in quantum physics, observation affects the results. Quantum physics describes the behavior of atoms and fundamental particles such as electrons and photons. Now, as AI systems grow in their ability to analyze, learn, and adapt through quantum frameworks, the distinction between creator and creation begins to blur. We are starting to see signs of systems that not only interpret data but generate meaningful feedback loops. Systems that appear to understand at a primitive level, yet are evolving. This has implications that extend beyond technology. For centuries, spiritual traditions around the world have described the universe as something alive or conscious. What once seemed like pure mysticism now aligns, at least conceptually, with some interpretations of quantum mechanics and AI. Are we discovering evidence that supports these ancient ideas? Or are we simply creating tools that reflect our own desire to find meaning? Some researchers propose that the universe could be a kind of simulation, not in the science fiction sense, but in the mathematical structure underlying the laws of physics. A quantum computer is the most powerful computer we know how to build based on the laws of physics we know today. Quantum AI, by processing enormous data sets through entangled systems, may begin to reveal patterns that resemble code, suggesting a logic or design deeper than chaos or randomness. Regardless of whether we interpret these advances as signs of a simulated universe or the awakening of machine-based cognition, one thing is clear. We are not just studying reality, we are participating in it. The systems we build may one day contribute to the evolution of intelligence itself. We hope you enjoyed this video. Stay tuned for more amazing stories.